Most important announcement I have tonight is that I brought a tablet, and I realize I can now, well, potentially scribble on slides, which I'm happy about. There may be some scribbling that I want to do today. So we're going to start, we're going to build on what we started last class with sampling distributions and put them to practice today with confidence intervals around a population mean and a population proportion from chapter 4 of the textbook. And then after introducing this, I'll introduce the t-distribution for confidence intervals and hypothesis testing from small samples. And I'd like to thank the majority of you who filled out the survey last time. I have actually analyzed the data and we'll be discussing it some today. Really nice having some new survey data to work with. So just to review, we got into last class sampling distributions and saw that they differ from the population distributions. They're related to the population distribution, but they're different. And if this broad peak here, let me just give this a try, see if I can. So if this broad peak here is the distribution of serum cholesterol of individuals in a population, and if we take a sample from that population and calculate their mean, do that repeatedly, we get a sampling distribution. And that sampling distribution will have the same mean as the population, but a different standard deviation, a different variance. And that variance is always smaller than the population because the average properties of groups are less variable than the properties of individuals. So the variance of this sampling distribution, this is a distribution that in real life we never observe directly, but it's something that we know something about the properties of theoretically, including from the central limit theorem, which relates the sampling distribution of means to the population distribution. And it had three parts. First one is that the mean of the population and the mean of the sampling distribution are identical. Sound good, Tony?
I'm sorry, I'm just checking it right now. Go ahead.
The second part is that the standard deviation of the population is related to the standard deviation of the sampling distribution by this simple rule that the standard error, which is the standard deviation of the sampling distribution, is equal to the standard deviation of the population divided by the square root of the sample size. So that tells us that the standard error of the sampling distribution is less, and it's less by a factor of 1 over square root of n. So for different values of n, as n increases, this variability of the sampling distribution gets smaller and smaller. And it's the same thing with proportions, as long as we have enough of a large enough sample size that that there aren't too many or aren't too few observations in either category. So if we were talking about cases and controls, the proportion and the sample size are such that we can use this normal approximation of the binomial distribution. And then in that instance, the standard error of the sampling distribution for proportions, it's the same, it comes from the same place as it did for continuous variables, except that this sigma is given by square root of p times 1 minus p. So we've done that before. We're just plugging this into the sampling distribution and the central limit theorem to apply the same thing to the large sample binomial distribution estimation. So the sampling distribution tells us the distribution of sample means under repeated sampling. So the sampling distribution tells us the distribution. Sounds like we have sound. Good. So this tells us everything that we need to know for doing inference from the sampling distribution in instances where we're drawing from either from a normally distributed population, or we have a large sample size such that the sampling distribution is normally distributed. That was the third part of the central limit theorem. Then we know everything about this sampling distribution. We know the mean, it's the same as the population mean, and we know the standard deviation, which, as long as we know the population standard deviation, is given by this formula. So how do we use this? First important application is to the estimation of confidence intervals. Now, a point estimate is what we would call our best guess for the population parameter. So in the example of the serum cholesterols, we take the mean of all of the serum cholesterol levels from our sample. If we were to make our best guess at the population average serum cholesterol, we would use that mean of the sample, since we know that on average, the mean of the sampling distribution, so the mean of the samples repeated many times, is the same as the mean from the population. But it doesn't tell us anything about how close we expect that to be. We know that the larger our sample size, the smaller the variability of the sampling distribution, and so the more confident we could be that it's close to the population mean, but we haven't quantified it yet. Conversely, if we only took like a sample of n equals 3, then there's still quite a bit of variability in that sampling distribution, so we could expect fairly large fluctuations from the true mean. And that's where these estimates of confidence intervals come in. And so in addition to that point estimate, we're going to estimate an interval where we think that the true mean lies. And that incorporates what's called a margin of error that will help us gauge the accuracy of around that point estimate. So I asked you to guess my age and to give both a point estimate, as in your best guess, and to give a couple of different confidence intervals around that to represent your uncertainty in that guess. We'll get to that in a bit. So just as an actual public health motivating example, suppose we have a random sample, n equals 309. So this is properly a statistically random sample from the population, and we have weighed each of these infants and calculated a mean birth weight of 119.6 ounces with a standard deviation of 18.2. And I talk about two examples here of whether that standard deviation is either known from the population or estimated from the sample. And then ask these two questions. What is the average birth weight of infants in the population? Well, our best guess is going to be 119.6. But then our second question is going to be, what is the 95% confidence interval on that estimate of the average birth weight. So we want to give an interval that we are 95% confident contains the true population mean. And I want to emphasize this. This is not the interval that contains the birth weights of 95% of the infants. I want that to be really clear, and that's something that we'll be testing to make sure that you're clear about that distinction. Anyone have a question about that?
So it's just a range.
It's just a range.
Yeah.
Yeah. So from your first few classes, you would have learned how to, given this mean, this standard deviation, to convert, to calculate. So you know that the 95% of the probability of the z distribution lies between minus 1.96 and 1.96. You could have converted that into weights. So 119.6 plus or minus 1.96 times 18.2. And that would have given you a 95% interval that contains the birth weights of 95% of all infants in the population. So you already know how to do this second thing, but it is not the same interval as the one that's going, that you're 95% confident that the mean lies in. Right? That was about individual infants. We're asking about now the mean in the population. So here's a question for you. Do you think that this answer, this 95% confidence interval, is that going to be bigger or smaller than this thing that it is not? Smaller. Yeah, it's going to be a lot smaller. Right? Because we're talking about, this is a mean of 309 infants. That's quite a few. So the variability of those means is going to be a lot less than the variability of individual infants. Mm-hmm.
So isn't the mean 119, not 309? Is it 309 the sample size?
Oh, sorry. Yeah, the mean is 119.6.
Okay.
The standard deviation of the individual birth weights is 18.2 ounces. So as just a quick spoiler on this, what is the standard error? So the variability of the sampling distribution if you were to take repeated samples of n equals 309.
The actual number or the formula?
Oh, the formula.
You would take 119.6 and over.
This is the mean, remember, not the standard deviation.
I mean, I'm sorry, 18.2 over the n squared.
Over the square root of 309.
Yeah.
Yeah, which will be somewhere around 16 or 17. It's the square root of 309.
17.5.
Okay. So the standard error is only going to be around 1 ounce. Okay. So how do we construct a confidence interval from a sample? We start with the point estimate. That's our best estimate. If we had to give like a single value for where the population mean is likely to be closest to, it would be at the sample mean, because we know that the mean of the sampling distribution is the same as the mean of the population distribution. Then we'll calculate a margin of error, the uncertainty above and below that point estimate, using the central limit theorem and that formula that we learned for the standard error. By the way, there are some online calculators which are kind of nice just for playing around and getting some feel for the relationship between these things, like the relationship between standard deviation, sample size, and standard error. So the margin of error is how far above and below the sample mean that 95% of the probability lies. And we can use a normal distribution to estimate that either for some very large sample or if sigma is known, as opposed to being estimated from the sample. If n is not so very large and we estimate the standard deviation from the sample, then that is an application for the t-distribution, which we'll get to later. So all we have to do from it, if we're able to use the normal distribution, is to take that sample mean, and the standard, or the margin of error is just 1.96 times the standard error. Or in general, the z-score for alpha over q for any other confidence interval. So for 0.05, i.e. the 95% confidence interval, you look up the z's, the z quantile for 0.025. If you want the 99% confidence interval, you would look up the z-score for 0.005 percentile. And then this, you relate this, you convert these z-scores using the standard error of the mean, which is sigma over square root of n for a continuous variable, or this for the binary variable. A couple things that the 95% confidence interval does not tell us. One, as I mentioned, it does not imply that 95% of the population values lie within these limits. And it also does not account for bias in that point estimate, either because we're using a faulty scale that undermeasures weight, or because we have a biased sample where we're tending to get underweight babies, but not more frequently than normal or overweight babies, for example. What it does do is provide an interval within which we're 95% confident that the true population mean lies. Or alternatively, if we were to take repeated samples, 19 out of 20 of those random samples would give us a confidence interval that contains the true mean. So one time out of 20, when we take a sample of this size, it should not contain the true population mean. Now, keep in mind, what we are not doing is giving like an error on, or a variability on the population mean. We assume that that is a fixed point value. We just don't know what it is. But it doesn't have error. It doesn't have spread, nothing like that. Population mean is just one value. So it doesn't have error or variance. This is a frequentist worldview. But again, if we took repeated samples and constructed 95% confidence intervals around every sample mean, if we did it correctly, and if our assumptions are valid, like our statistical random sample, and our assumed distribution of the sampling distribution, then 95% of those samples, the interval would contain the true population mean, and 5% would not contain the true population mean. This is just an example from a simulation where these are samples of a continuous variable drawn from a population mean, which is right here. And from each sample, I've calculated a 95% confidence interval. And I'm showing here, what is this, 200 intervals, and about 10 of them do not contain the true mean. So what you'll see about them is that these confidence intervals from individual samples, they both shift left and right, and some are bigger, some are smaller. That's because in sampling error, the mean can change, the variability can change. Both of those affect this 95% confidence interval. But regardless of the fact that they're moving left and right and getting larger and smaller, 19 out of 20 of them contain the true population mean. Of course, you never actually take 20 samples when you're doing a study. You only get one sample. So you only see one of these, and you have no way to know whether it's one like this, that it's off, you got unlucky, it does not contain the true population mean, or more likely, it's one of these, because 19 out of 20 of them are like that, and they do cross the true population mean. So as long as you've done everything right, your situation will look like this. Yeah.
Trying to figure out what this is actually.
So let's say these are
Red and then there's black. I mean, I see the view in the middle, but I don't get that.
the reds are the errors. So this one is like a type 1 error where it looks like the true population mean is in this interval, but it is not. So if we were doing a hypothesis test, and I'll talk later about the equivalence between confidence intervals and hypothesis tests. Our null hypothesis was that the mean, say, weight of the population from which these infants were drawn was equal to mu, if this is like the normal value in the population, and we're looking at some other smaller population with, coming from a particular area or mothers with some attribute, then our null hypothesis might be that the mean infant weight is the same as for the entire population. We did a study, we took some small sample, and it produces a confidence interval like this, then we will commit a type 1 error, because we will think there is a difference between our population and the null hypothesis population, when in reality there's no difference. It was just the luck of random sampling. So the reds are the ones where we make an error, confidence interval does not contain the true population mean, and the blacks are the one where there's no error. We would correctly accept the null hypothesis. Okay, let's take a look at these results. Don't be scared, that's my data analysis. Let's just look at the results. Let's see. I need to go full screen. Okay. So I sorted these from the forget how I sorted these. I could look, but they're roughly sorted from younger guesses to older guesses. And I put on here the point estimate. These are your actual data. If you filled out the survey, then your response is here. So here there were 3 people who all guessed I was 35, and then they put 50% confidence intervals. These two are about the same, and somewhat larger 95% confidence intervals. So there's some good attributes about these guesses that are worth pointing out. One, the thing that is good is that both of the confidence intervals contain the point estimate. That's good, right? Because certainly your most likely guess should fall somewhere within your confidence interval. Another good thing I see about these is that the 95% confidence interval is bigger than the 50% confidence interval. And that makes sense because if you want to be 95% confident, you need to provide a bigger range. If you said between 0 and 100, then you could be 100% confident. Okay. And what you see here, like the difference between this third guess and this first one is a difference in confidence. This person is very confident in their ability to guess my age, and this person is less confident in their ability to guess my age. Maybe I should use a different word than confidence here. They both have the same confidence. They both have 50% confidence and 95% confidence, but they both have different estimations of their ability to guess ages. So this one feels they have less ability to guess ages and need a larger confidence interval to have the same confidence. We see some other interesting properties going up here. Like this one is asymmetric, so there's a greater margin of error going below my age than going above. And that's certainly something that is possible. We won't estimate that kind of confidence interval using the normal distribution or the t-distribution because they're symmetric. But it is possible in certain instances to have an asymmetric confidence interval. One obvious example would be if you had like, an upper limit, that I can't be older than this because, I don't know, something about me. But okay, going up, I see a couple of let's see, we can call them opportunities to learn. I can't draw in here. So this one here, this is number 10. Number 10 provides some opportunities to learn here. What's funny about this confidence interval? Sorry?
The point estimate is not within 50%.
Yeah, the 50% confidence interval does not contain the point estimate. So it's like the 50% confidence interval is just from like 35 to 36 years old, even though my most likely age is 40. So it doesn't really make sense. There's some other ones here. This one has a couple of issues. One is that the 95% confidence interval doesn't contain the point estimate, and the other one is that the 95% confidence interval is smaller than the 50% confidence interval. So I would rather get my 20-to-1 odds with this person because they're gonna give me a tougher guess at 20-to-1 odds than they would at even odds. Kind of looks like this person actually entered twice and put the same one in each time. Other than that, these look pretty good. One thing that I noticed some extreme difference on, here's another one that has the confidence intervals reversed, where the 50% confidence interval is larger than the 95% confidence interval. So this person, if they could find people to accept their even money bet, would probably do pretty good. They've really like hedged their bets here. But they found someone to take their 20-to-1 bet, I'd rather take their 20-to-1 bet. Same here. Does this make sense to everyone? And here's the overall estimate. I went and used the techniques that we just covered. I calculated the mean just from all of the point estimates. And then I calculated a 50% and a 95% confidence interval based on the my estimated margin of error from the variability in the sample. And it's actually quite a bit smaller than a lot of these estimates. There's probably some violation in this because I assumed that these are all independent samples, but looking at this, I would actually guess that at least one person entered twice. So those don't really look like independent observations. So, but overall, just at the points, you all think that I look 40 years old and have, if your guesses are unbiased, so they're centered around my true age, then the 95% confidence interval around my ages would be from about 37.5 to 42.5. Any questions?
Is that correct?
I want to say yes, but no, I'm
Is
actually,
that biased?
yeah, it actually is biased. No, I'm 45. So, but this has been interesting to me. I've actually been doing this survey now. I think this is the 6th year in a row, so I might have enough data now to do a linear regression, and maybe I'll bring together all of the data from the previous years for when we're doing linear regression to test against the null hypothesis that my apparent age is increasing by 1 year per actual year, or maybe the null hypothesis that I'm not aging at all.
Yes.
I'll get to find out if I'm a vampire. All right, I have a Q&A for you now. So is the 99% confidence interval larger or smaller than a 95% confidence interval?
I mean, yeah, I think it's small. So that means the window, right?
Yeah.
Yeah, it's small.
Someone explain to me why larger. I don't want you to explain smaller. Why is it larger?
Yes, I can explain well. It's larger because you want to have a larger range in order to have more have more chances that it's going to be
Within,
confidence.
Yeah.
It's going to be within.
If it's a larger range,
Yeah.
then,
Like your age, as I said, between 35 and 45 versus between 39 and 40. You know what I mean?
yeah, the larger it is, the more frequently you're going to contain the right answer. Just like, I don't know, just like, you know, if you have I don't know, you're playing basketball, you have a larger rim, you can get the basket in it more often. So you can be more, you know, have greater confidence that you're going to get the ball in the basket. So let's see. It's larger. So as the size of a confidence interval increases, does the confidence increase or decrease? Same question asked a different way. In a way,
Increases.
yeah. confidence. This pointer works as long as I never lift it off, otherwise I don't know where I'm about to draw increase. This is one that often trips students up, this second one, because they think that an increasing confidence interval means less certainty or less confidence, but that's not what I'm asking. I'm saying for a larger interval, you can have more confidence that it contains the right answer. And that is, so, yeah. As n increases, does the 95% confidence interval increase or decrease the size of the interval? It decreases. Because the standard error decreases, sigma over square root of n, the variability of the sampling distribution gets smaller and smaller. The less the sampling distribution will vary from the true population mean. And finally, what does the confidence interval tell us about the variability of individuals in the population? This is a tricky one. Nothing. These are all the kind, very good, nothing. These are all the kinds of like conceptual understanding that I really want you to have and that I'll try to test on the exam so that, yes, you need to be able to apply the formulas and calculate confidence intervals, but I really want you to have an understanding of them and be able to answer conceptual questions like this. So the confidence interval tells you about your confidence that the population mean lies in that interval is not an indication of individuals in the population. So just because a 95% confidence interval lies between here and here, the variability of individuals, well, it could be a little larger or a lot larger depending on the sample size. All right, so going back to that, we did this orally already to calculate a confidence interval in this infant birth weight example. We take the sample mean plus or minus the critical value, which in this case is 1.96 because the infants are, infant birth weights are normally distributed, and we have a fairly large sample size. That margin of error, so is 1.96 times 18.2 divided by the square root of 309 gave us 1.035, and multiplying that by 1.96, the critical value gives us this, which is the margin of error, 2.03 ounces. Quadrupling the sample size, this will have the margin of error, or increasing our level of confidence will require us to increase the margin of error a little bit. Yep.
In this page, the question 1 and 2, is this just illustrates the question on the previous slide? Question 3 is that the number of sample is larger and your estimate is more accurate, so the range is smaller.
Right. That's right. So yeah, when we increase the sample size, the standard error goes down, the margin of error goes down, and the confidence interval gets narrower.
So
the mean of the sample, the point estimate always will always be the mean point of the content.
As long as we're dealing with a symmetric sampling distribution, such as the normal or the t-distribution, then the mean of the sample will be at the center of the confidence interval. Good question. If there were an instance where say we were building a confidence interval on like the logarithm of a variable, if its logarithm was normally distributed, so we could use a normal distribution, then when you exponentiated it, the point estimate would no longer be in the middle of the confidence interval. I have a mini tutorial. There's this series of mini tutorials on our YouTube channel, and one of them is going through the calculation of a 95% confidence interval by hand. Okay, so we've been pretty fixated on the normal distribution, the binomial distribution, and the normal approximation to the binomial distribution. And we're gonna take a trip from those for the first time here with the student's t-distribution. So using the z-distribution is okay as long as we have a very large sample size, or sigma is known. And I say not just large, but very large, because even in like when we are deciding to use something like a t-test, we often talk about n equals 30 as being a large enough sample that that we can use the assumption of a normal population. But even in that instance, we will tend to have an underestimate of the confidence interval, or the margin of error, if we use the z-distribution. And the reason is that we have some uncertainty in the variability. And to account for that is where enters this so-called student's t-distribution, which came from this guy, William Gossett, back in the early 20th century as an employee for Guinness. And I guess he wasn't allowed to publish his findings, but he knew this was an interesting and an important statistical finding, so he published it under a pseudonym, where his name was Student. So he developed it for quality control of small numbers of batches of beer. So you take some small number of samples, and you wanted to be testing a null hypothesis that these small batches were no different than what is expected, say for alcohol content or other properties that he was aiming for in the quality of the beer. And you notice that using a normal estimation, even though these were normally distributed properties like the alcohol content, that he was rejecting this null hypothesis with an incorrect frequency, not correctly controlling for type 1 error. So that is, the sampling variability in these small batches was greater than expected, not because of the beer, but just because he had small sample sizes. So to calculate it, it's calculated in just the same way as the z statistic. The only difference is that we call it a z statistic when the population standard deviation is known and we use it, and we call it a t statistic when we don't know the population standard deviation and we instead estimate it from the sample. So we're estimating not only the mean, but the standard deviation using this sample of ours. And that's a pretty common case. Usually we don't know the population standard deviation. And instead we have to estimate it from the sample. Then we estimate this standard error as being the standard deviation is estimated from the sample divided by the square root of n. But the difference is this statistic that we calculate from here is not normally distributed unless n is very, very large. But instead its distribution follows this distribution that we call the t distribution, or the student's t distribution. So supposing we draw a statistically random sample of size n from a normal distribution with mean mu and standard deviation sigma. And then from that sample, we calculate this t statistic from the mean of the sample divided by a hypothesized mean under the null distribution divided by the standard error as estimated from the sample. Then this t statistic follows a t distribution with n minus 1 degrees of freedom, where n is the sample size. So it's a little more complicated than the z-test, and when we were doing this with the normal distribution, because there's a different t distribution for each sample size. But the density curve of this distribution looks kind of similar to the normal. It's also symmetric about 0, and it's also bell-shaped. And the more degrees of freedom we have, the narrower the spread of this t distribution. And furthermore, as we get to a very large number of degrees of freedom, it narrows down to the normal distribution. So the t distribution with an infinite number of degrees of freedom, or 1,000,000, mirrors the normal distribution. But the smaller the number of degrees of freedom, so sample sizes of, coming down from 1,000,000 to 100, 50, 20, 10, 3, that t distribution gets wider and wider. This is what the table looks like in your textbook. It's a little bit more complicated than the z-tables. Because instead, you remember you had, you used the vertical and the horizontal just to look up a precise value of z, and then it would give you the probability under the entry. Whereas in this table, it's only going to give you several probabilities. So under two tails, 0.01, 0.02, 0.05, 0.1, and 2. And it gives you the critical value under both, if it's the two-tail value, or under just the right or the left-hand side for the one tail. So it doesn't give you as much flexibility because it has to give you values for all of these different degrees of freedom. But if we take a look at this one, our too difficult. Okay. We take a look at this column with a probability of 0.05 under the two tails. This is what we've been using for 95% confidence intervals. It's the one that we'll use for t-tests with a p-value or an alpha of 0.05. You see down here under n equals 30, it's pretty close to the 1.96 we're used to. Over here at infinity, it is exactly 1.96. The smaller the number of degrees of freedom, the larger this critical value gets. And down to 1 degree of freedom, it's huge. It's 12.71. So what does this mean? If you have a sample size of n equals 500, then to 2 decimal places here anyways, a confidence interval that you calculate from the t-distribution is going to be the same as it was from a normal distribution. You go down to 400 degrees of freedom, it's just 1 decimal place larger. But as you get fewer and fewer degrees of freedom, even at 30 degrees of freedom, it's kind of substantially larger, this confidence interval. 2.04 critical value instead of 1.96. And of course, once we get down to, say, 5 degrees of freedom, there's a really big difference. So what's the practical effect of this? In instances where you're estimating a standard deviation from the sample, your variability of that statistic is larger. Your sampling variability is larger. That's what the t-distribution accounts for. You have uncertainty both in the mean and in the estimated standard deviation. So you need to know how to calculate degrees of freedom. This will be a recurring theme in your statistical classes, and this one and going forward. It's simple for this student's t-distribution. All it is the number of independent observations minus the number of parameters estimated during intermediate steps. Another maybe more intuitive way to think about it is that if you know the value of the statistic, the degrees of freedom is n minus the number of observations you could recover if you lost those measurements. So knowing let's say you had 3 observations. If you knew the mean and the standard deviation of them, you would only need 2 of them, and there's only one value of that third one that could give you that same mean and standard deviation. And the number of parameters is just intermediate steps, so just either the mean or the standard deviation. When do you use the t-distribution? You can use the t-distribution for, so first, if you have a normally distributed population, your values in the population are normal, then even with sort of large-ish, like greater than 30 observations, you still use the t-distribution for confidence intervals and for hypothesis testing, just using a critical value from a t-table instead of from the z-table. That's because, as you saw, even for like n equals 100 or 100 degrees of freedom, there's still a noticeable difference between t and z. All right, so here's an example. I've taken 5 beers and measured the alcohol content in each one of them, and I want to know what's the 95% confidence interval for the alcohol content produced by this procedure. That would be the confidence interval question you might ask. From a hypothesis testing perspective, you might ask, is there evidence against the null hypothesis that the population average alcohol level is 5.0 at an alpha type 1 error rate of 0.05? So if I were going to actually go through this, for the 95% confidence interval, I would calculate the mean of all of these, the standard deviation. I would divide that standard deviation by square root of 5 to get the standard error. Then I would use 4 degrees of freedom, go back to this table, and see that the critical value is 2.78. So I would multiply that standard error by 2.78 to get a confidence interval. And I won't actually go through this now because you'll have plenty of time to practice during the lab today. There are a couple of assumptions of these T procedures. The first one, as always, is that the data come from a statistically random sample. And the second is that the population is approximately normally distributed. However, these T procedures are quite robust. And by that, I mean that its outcome is not very sensitive to violations of these assumptions, particularly around the assumption of the normally distributed population. So granted, real populations often have, whatever you're measuring, have some deviation from normality. But the two-sided T procedures in particular, meaning that you're using both tails of the T distribution for your calculation, are quite robust against departures from normality, except in the case of there being extreme outliers in the population or strong skewness, like a very long tail under one end. So they're robust and they're also conservative in that your p-values and your confidence intervals tend to increase when the normal assumption is violated. So you're not likely to make type 1 errors. You're not likely to be overconfident in your results as a result of these violations. You're actually more likely to not have as much confidence or as much certainty as you could. There is an exception that the one-sided tests, where you're just doing inference using one tail of the distribution, don't work as well as two-sided tests when you have a skewed population. Those are really rare that you're going to do one-sided tests. I will talk about them some more once we get to hypothesis testing. So some practical guidelines. If you have a sample size, we're talking about inference on a mean, like with the beers. If you have a small sample size, less than 15, then go ahead and use the T procedures if the data you observe are close to normal. Otherwise, they're non-parametric alternatives, which I'll tell you about later, even though we don't actually apply them in this class. But for all of the T-based procedures, there are alternative so-called non-parametric tests, which don't make any assumptions about the distribution in the population. If you have a large sample size, say greater than 30 or 40, you can still use T procedures quite reliably, even for clearly skewed distributions. And you can use some of the plots that you've learned for continuous data to investigate these properties. But the assumption of the statistically random sample is always important. really robust to this violation. You don't have a statistically random sample. There can be bias. There can be so-called pseudo-replication if you think that your observations are independent, but they're actually repeated observations, like we saw in those couple of guesses. You are likely to be overconfident if you have not a statistically random sample. All right, some more Q&A. So when we're calculating a confidence interval from the t-distribution, when we are estimating the standard deviation from the sample instead of knowing it from the population, we use the t-distribution. True or false? True. Very good. That was an easy one. Is the 95% confidence interval larger or smaller when using the t-distribution compared to when using a z-distribution? What's that? Larger, yes. Larger. As n increases, the t-based confidence interval becomes more similar to the z-based confidence interval. True or false? True. Very good. All right, time to wrap up. So just to summarize, the confidence interval gives us a likely interval to contain the true population mean. So a 95% confidence interval contains the true population interval 95% of the time. And to be very confident, to have high confidence, requires a large margin of error. So the 99% confidence interval must be wider than the 50% confidence interval. Your best point estimate from a sample is at the middle of the confidence interval, as long as we have a symmetric distribution. The standard error in the confidence interval, they don't tell you anything about the variability of the population. They're all about your uncertainty in your estimate of the population mean. And when we're doing this from a small sample, we use the t-distribution for normal populations. Any questions before we take, say, a 5-minute break? Yes?
I want to know the reason of why the t-distribution can closer to the normal distribution when the rate of freedom increase. Is whether that the standard deviation we can get from samples can be closer to the sigma population when the sample size is.
Yep, that is true. The larger your sample size, the closer your estimate of the standard deviation will be to the population standard deviation. For n equals 500, your estimate of the standard deviation will be very close to that of the true population standard deviation. Another way you can think of it is that, the uncertainty in your estimate of the standard deviation when you estimate it from the population increases the variability of that t statistic. When you're calculating like the difference in means divided by the standard error, you have additional uncertainty in that denominator that causes more variability in your statistic that you're calculating. But yeah, as your sample gets larger and larger, the less that uncertainty in your denominator. Any other questions? All right, thank you.